mathematicians. This is part 2 of the our series of videos on diagonalizability of matrices. Okay, so today we see many sufficient conditions for diagonalizability of a matrix. Yesterday we saw one important necessary condition for diagonalizability of a matrix. What is that? If you want to diagonalize a matrix over a field F, in the very least, it should have all its eigenvalues in the field F. Okay. So if you have a real matrix, if its eigenvalue should be in R, okay, that is a necessary condition for diagonalize a matrix over R. But again, if you have a real matrix, its eigenvalues are in R, that doesn't mean that the matrix is diagonalizable over R. For example, it can have all the eigenvalues are equal. Yesterday we saw one example of a matrix whose all eigenvalues are equal to 5. That is a non-diagonal matrix with all its eigenvalues are equal, therefore it was not diagonalizable. Okay. Okay, so having eigenvalues in the base field is a necessary condition, not sufficient. Now we're going to see many sufficient conditions for diagonalizability of matrices. Okay, first we have a theorem. So again, whatever theorem results I'm quoting here, very much I try to give proof also. Whichever I'm not proving, that you can find from the books Linear Algebra by Friedberg. Okay, so the author name is Friedberg. So this is Linear Algebra by Friedberg. Another book is the very standard Hoffman and Kunze. Okay, so two books, both the title is Linear Algebra. Okay, so what is the statement of the theorem? Let A be an n by n complex matrix and A star be the conjugate transpose of A. What is conjugate transpose? It is A bar transpose. So A bar means, so it is a complex matrix. You can take the conjugate of all the entries of the matrix. Then you take the transpose of the matrix. And if the matrix A satisfies A star equal to A star A, then A is diagonalizable over C. Okay, such matrices are called normal matrices. Okay, so normal matrices. Normal matrices. So normal matrices are diagonalizable over C. If you noticed, like symmetric matrix, we saw symmetric matrix even diagonalizable over R, but you can talk about complex symmetric matrices. Okay, so that satisfies A equal to A transpose. Okay, so now if that matrix satisfies the condition A star equal to A star A, then such matrices are also diagonalizable over C. Okay. Okay. Now we define what is a minimal polynomial of a matrix. Uh, so the least degree polynomial satisfied by A. That is what is defined to be minimal polynomial of A. Okay. So so we denote the minimal polynomial of a matrix by MA of X. But how do we know the least degree polynomial is exist for a matrix A? That is true because by Cayley-Hamilton theorem, if A is a matrix of order, it is a two, if it is a matrix of order n, then you can always find the n by n degree n polynomial which satisfied by A. Okay, so we'll do one example. So again, we work with our so yesterday also, if you noticed, this matrix played a very important role in our yesterday's lecture. So you consider this matrix. This matrix has characteristic polynomial x square plus 1 that you can easily see. Now this is my A and we calculate A square. What will be A square? So you 0 1 minus 1 0. So if you multiply, what will you get? 0 1 into this, you will get minus 1 minus, then again you will get 0. This is 0. This is minus 1. So A square will be minus 1, 0, 0, minus 1. So you get A square plus, if you add identity matrix to this matrix, you get a 0 matrix. That means that in the polynomial x square plus 1, in place of x, you substitute a. In place of the constant term, you substitute identity matrix. Okay, so for example, you take x square plus, you take 2 here. Then the characteristic polynomial will be x square plus 2. Then we calculate its square. Okay, what will be the square? You will get minus 2 here. Again, you will get minus 2 here. So a square will be, so you have to add it. So this is minus 2i. Okay, so this is minus 2i. So you have to add plus 2i to get 0. Okay, and so the characteristic polynomial is x square plus 2. So in place of x, we substitute a, and in place of 2, you have to add 2y. So a square plus 2y, we get 0. So the point is, with the constant term, you have to add that much identity. That is the point I'm trying to make. Okay. So if it is a 2 by 2 matrix, we get a polynomial of degree 2 satisfied by the matrix A. But this may not be the smallest degree polynomial satisfied by A. Okay. There can be a degree 1 polynomial satisfied by A. If there is a degree 1 polynomial satisfied by A, and then that is the least degree polynomial satisfied by A, we call it the minimal polynomial of A. Okay. So if in general, for example, A could be a degree 10 polynomial, is a maybe 10 by 10 polynomial. So the characteristic polynomial will have degree 10, but the least degree polynomial satisfied by A could be of degree 3, 2, 1, or any number between 1 to 10. Okay. So the least degree polynomial satisfied by A is what we call the minimal polynomial of A. Okay. Okay. So we know what is a minimal polynomial. So let's write down some properties of minimal polynomial. So minimal polynomial divides all the polynomials satisfied by A. Okay. So this is a very easy exercise. Since it is a least degree polynomial, it, it should divide all the polynomial which are satisfied A. In particular, minimal polynomial divides the characteristic polynomial of A. Okay. Suppose, let's come to the second point. Suppose f of x is some polynomial, divide another polynomial g of x. Okay. So f of x divides g of x means we can write g of x as f of x times h of x. Okay. Now, if alpha is a root of f of x, then alpha is also a root of g of x, because once you substitute alpha in f, right hand side will be 0. Therefore, left hand side also has to be 0. Okay. So if f divides g, then all the root of f of x are roots of g of x. Okay. So now minimal polynomial divides characteristic polynomial. That is what we just saw. Therefore, all the roots of minimal polynomial are the roots of characteristic polynomial. But what are all the roots of characteristic polynomial? They are precisely the eigenvalues of A. Therefore, the roots of minimal polynomials are actually eigenvalues of A, and all the eigenvalues of A are occur as a minimal polynomial of A. Okay. So every root of minimal polynomial is an eigenvalue of A follows from this argument g of x equal to f of x times h of x. That argument it follows, but every eigenvalue of A, or every root of the characteristic polynomial is also a root of minimal polynomial. That requires proof that you can check in the linear algebra books that I suggest, or in the subsequent lectures we will talk about uh, uh, Jordan canonical form, all these things. So that time it will be more clear why every root of the characteristic polynomial is also a root of the minimal polynomial. Okay. Okay, good. Now, okay, so now we come to that point. It is an important point. Find all complex matrices whose minimal polynomial is x minus alpha. Okay, so we're going to solve some problems in which we need this fact. So we are proving it. So you can pause the video here and you try to find what are all the complex matrices whose minimal polynomial is x minus alpha. And yeah, please pause it and you check. And I'll give you the answer. So you see, suppose x minus alpha is a minimal polynomial of a, then a satisfies this polynomial because it is a minimal polynomial. So what we get in place of x, you have to substitute a. In place of scalar, you have to substitute constant times scalar as that constant times you have to put identity. Okay. So we get a equal to alpha times identity. So that means that what is alpha times identity, how such matrix are looks like. So basically it is a scalar matrix whose diagonal entries are equal. For example, this is 2i. Okay. So it is a diagonal matrix whose all the diagonal entries are equal. Alpha. So all the diagonal entries are equal to alpha. So A is a scalar matrix. Okay. Therefore, x minus alpha is a minimal polynomial implies A has to be a scalar matrix. Now, you take alpha equal to 0. If you take alpha equal to 0, we get A equal to 0 times I. 0 times I means A equal to 0. A equal to 0 matrix. Therefore, x is the minimal polynomial of A implies A equal to 0 matrix. Okay. Yeah, so we know when x minus alpha is a minimal polynomial. That is precisely when A is a scalar matrix. Okay, let's continue. So, okay, next we have a theorem which is necessary and sufficient, which gives a necessary and sufficient condition for diagonalizability of a matrix. Okay, so you consider linear transformation A from V to V, then A is diagonalizable if and only if there is a basis of eigenvectors of A in V. Okay, so basically what this theorem states is if the matrix is diagonalizable, then you can find a basis of the vector space V whose elements are whose all the elements are eigenvectors of A. Okay, so you just go through the proof. It is very simple proof, and we continue. Okay. I mean, a proof is not such a tricky proof, it's just straightforward proof. You assume that it is diagonalizable, then you will get a basis of eigenvectors. Conversely, if you assume there is a basis of eigenvectors, then you get the matrix is diagonalizable. Okay, good. So, next, I'll state a couple of important results, and we will prove these results when we talk about Jordan canonical form in our consequent lectures. So, first result is eigenvectors corresponds to distinct eigenvalues are linearly independent. So this is simple result. So we will prove this result now. So we assume that let V1 and V2 be two eigenvectors of a matrix A corresponds to the eigenvalues lambda 1 and lambda 2. We assume that lambda 1 not equal to lambda 2. It means that they are corresponds to eigenvalues corresponds to distinct eigenvalues. So we claim that V1 and V2 are linearly independent. So suppose alpha v1 plus beta v2 equal to 0. To prove v1 and v2 linear independent, we have to prove that alpha and beta equal to 0. Okay. If we prove alpha and beta both 0, then v1 and v2 are linearly independent. So suppose alpha is not equal to 0. Okay. If beta is not equal to 0, the same proof will work. So we just assume that alpha not equal to 0 without loss of generality. Then we'll get v1 equal to minus beta by alpha times v2. Right. So this is possible since alpha not equal to 0. I take the quotient as this minus beta by alpha. I take it as some scalar gamma. We get v1 equal to gamma times v1 equal to gamma times v2. Now let's calculate what is AV1. AV1 equal to for V1 we substitute this value A gamma times V2. Now gamma is a scalar, we can take it this side. We get gamma times AV2. Now what is AV2? You see V1 is an eigenvalue for the V1 is the eigenvector for the eigenvalue lambda 1. V2 is the eigenvector corresponds to the eigenvalue lambda 2. So we get a V2 equal to lambda 2 V2. Now again, this gamma we send it here. We get lambda 2 times gamma V2, and we get what is gamma v2? We get gamma v2 is v1. So we get a v1 equal to lambda 2 v1. So it says that v1 is an eigenvector for the eigenvalue lambda 2. But v1 is an eigenvector corresponds to the eigenvalue lambda 1, and we know that lambda 1 is not equal to lambda 2. So that is a contradiction. This contradiction happens because we assume that alpha not equal to 0. Therefore alpha equal should be 0. If beta equal to 0, the same similar argument will be you can work it out. You take v2 equal to minus alpha by beta, and you proceed, you will get a decide contradiction. So we have proved that the eigenvectors corresponds to distinct eigenvalues are linearly independent. And the next result is if a matrix has distinct eigenvalues in a field F, then it is diagonalizable over R. This is the result what I was telling. When we do Jordan canonical form in our consequent lectures, we prove this result in a much simple manner. Okay, so we continue. So we do some problems. Yeah, these are all previous year CSR problems. Okay, let f of x be the minimal polynomial of a 6 by x 6 matrix. So this is a 6 by 6 matrix, and f of x is the minimal polynomial. Then what is the rank of the matrix f of a? So you please pause the video. It is a very simple question. So you please pause the video and think about it for a couple of seconds. Okay, I hope you got the answer. I mean, it is very simple. The answer is 0 because every matrix satisfies its minimal polynomial. Therefore, once you substitute, say this is my matrix A. Once you substitute the matrix A in its minimal polynomial F, then f of A will be 0 matrix. Okay, that is what it means to say A satisfies minimal polynomial. What is the rank of the matrix? What is the rank of 0 matrix? It is 0. Okay, therefore the answer is 0. So this is one CSR part B problem. Okay, similarly, since we are talking about this matrix, we do the same matrix is asked in some other year also. So we do. What is the determinant of the following matrix? So again, think about. Please pause the video. Think about it for some time, and then you continue the video. Okay, so I hope you guys got the answer. So the thing is, it is in the block matrix form. So I have given a above formula. I have given a formula here to calculate the determinant of block matrix. So determinant of A, B, C, D equal to then. So here this D is invertible. That is the important thing. D is invertible. Therefore, we are writing this determinant of D times determinant of A minus BD inverse. So sometimes in this block form, this D may not be invertible, but this A might be invertible. Then you have to modify this formula suitably. So please check what is the analog formula for A. Okay. Now, anyway, we got in place of D, we got identity matrix. So we can use this formula. So determinant of ABCD equal to determinant of D times determinant of A minus BD inverse. So this you see B is this simple matrix. Again, D is identity matrix, therefore its inverse also identity matrix. Again, C is this simple looking matrix. So you can easily calculate A minus BD inverse, and so it is A minus BD inverse is a 3 by 3 matrix, and its determinant can be easily calculated. Determinant of D is 1, so because D is identity, so you can easily calculate the determinant of this block matrix. Okay, so let me know the solution, let me know the answer in the comment. I'll be very happy. Okay, let's continue. Again, which of the following are eigenvalues of the matrix? Okay, so please pause the video here, and immediately you can eliminate two options from whatever we have seen in yesterday and today's video. Okay, remaining two options only require little bit work, that I will tell. If you got all the answers, so it is a part C question. So that is important. It is a part C question. So more than one option can be correct. Okay, so okay, if you guys got the answer, it's very good. Like, so you see it is a symmetric matrix. So for real symmetric matrix has all its eigenvalues are real. Therefore, I and minus I cannot be roots. And what happens is 1 and minus 1 are actually eigenvalues of this matrix. So how to see 1 is an eigenvalue? One simple method to see is so I already I have done a problem. So I have give link to uh, the problem in the description, or you can see above also. So what is the result? If a matrix has a constant row sum, okay, you see all the rows has a row sum equal to 1. Okay, so the row sum is constant, and all and each row sum of each row is equal to 1. Okay, if so, the precise result is if A has constant row sum L, then L is an eigenvalue of A. Eigenvalue of A with eigenvector all one vector. Okay, so this is one standard result. As I said, I have given link to proof of this result, and you can see the description also, where there is another CSR problem where this same result you can use to solve that problem. And please check that problem. That problem is very interesting. Okay, therefore, since this matrix has constant row sum and the constant row sum is 1, by this result we get 1 is an eigenvalue. But there is a straightforward method. Without using any result, you can prove that 1 and minus 1 are eigenvalues. So let me explain you that result. So now this is our matrix A. So for this matrix, 1 is an eigenvalue means you have to find the eigenvector. Okay. Lambda is eigenvalue if you can find x not equal to 0 such that ax equal to lambda x. So if 1 is an eigenvector means you can find a non-zero vector here such that ax equal to 1x. So now x is a x1, x2, x3, x4, x5, x6. Okay, it is a 6 by 6 matrix, so it is a 6 by 1 vector. Now, if you multiply the left hand side, you will get x4, x5, x6, x1, x2, x3. Right hand side is one time this vector is the vector itself. You get x1, x2, x3, x4, x5, x6. So, equating these two vectors, you get x1 equal to x4, x2 equal to x5, x3 equal to x6. So, for example, you can take this vector x1, x2, x3, x4, x5, x6 to be 1, 2, 3, 1, 2, 3. Then it will satisfy x1 equal to x4, x2 equal to x5, and x3 equal to x6. Okay, or you can take everything equal to 1. 1, 1, 1. If you take all the entries to be equal to 1, then clearly that will satisfy this condition. Okay, so we get a non-zero vector satisfying ax equal to 1x. Similarly, you can do ax equal to minus 1x also. You ax equal to minus 1x also, you will get to the non-zero vector x. Okay, so basically you will get x1 equal to minus x4, x2 equal to minus x5, x3 equal to minus x6, and 1, 2, 3, minus 1, minus 2, minus 3 will be an eigenvector. Okay, therefore minus 1 will also be an eigenvalue. Okay, so please check, and please check the description for the another problem using the constant row sum idea. Okay, okay, let's continue. Okay, so this is again, this is a main result in the diagonalizability of matrices. A matrix is diagonalizable if only if its minimal polynomial splits into distinct linear factors in F. Okay, so we'll prove all these important results, but we need to develop some tools. Okay, so once you develop the tools, so basically that I'm going to roughly say about what is Jordan canonical form in the subsequent lectures. Once I tell what is Jordan canonical form, all the results will follow immediately from that. So we skip the result proof of this result for the time being, but we solve the problems. Okay, right. So we saw this matrix 0, 1. Oh, consider this matrix 0, 1, 0, 0, and for this matrix, if characteristic polynomial will be x square, and its minimal polynomial should divide the characteristic polynomial. So the possible minimal polynomial is x and x square. Okay, but this cannot be minimal polynomial because we saw that x is a minimal polynomial if and only if the matrix is a zero matrix. But this is not zero matrix, therefore the minimal polynomial has to be x square. Okay, so for this polynomial, characteristic polynomial equal to minimal polynomial. Okay, so if somebody asks you in some interview or some place where to give an example of a matrix for which a characteristic polynomial equal to minimal polynomial, you can give such a simple example. Okay, now this minimal polynomial is not a product of distinct linear factors, because one linear factor is occurring twice, x into x. Okay, since linear factors are repeating, this matrix is not diagonalizable. Okay, so I hope you understand. So this result is very powerful. Let's continue. Okay, some CSR problems using this result. Diagonalizable over F if and only if its minimal polynomial splits into distinct linear factors. So if A is a complex n by n matrix with A square equal to A, if you see some previous year CSR problems, you can see many problems in which they are asking about the matrices satisfying A square equal to A, and they will give you some options and you have to eliminate options and you have to pick the correct options. So this A square equal to A, matrices satisfying A square equal to A, is very important. We will see how to tackle problems involving the matrices satisfying A square equal to A. So we have a matrix satisfying A square equal to A. So A square equal to A means A square minus A equal to 0. This implies A into A minus I equal to 0. So that means that A satisfies the polynomial x into x minus 1. Okay. So A satisfies x into x minus 1, and we saw that minimal polynomial divides all the polynomials satisfied by A. In particular, minimal polynomial should divide x into x minus 1. Okay. Now, what are the divisors of this polynomial x into x minus 1? X is one possibility, x minus 1 is another possibility, x into x minus 1 is another possibility. These are the only three polynomials that divides x into x minus 1. So if x is the minimal polynomial, then A should be 0 matrix. If x minus 1 is the minimal polynomial, then A equal to identity. Okay, that is why we initially we check what we found all the matrices for which x minus alpha is the minimal polynomial. Okay, so now if x into x minus 1 is a minimal polynomial, now this is a product of distinct linear factors. Okay, therefore we get in this case matrix is diagonalizable. And what are all the eigenvalues of A? Eigenvalues of A are 0 and 1. So we also saw that every eigenvalue of A is an root of minimal polynomial. Every root of minimal uh, every eigenvalue of A occur as a root of the minimal polynomial. So from that we conclude that for a minimal polynomial x into x minus 1, the roots are 0 and 1. Okay. Therefore, for A also the eigenvalues are 0 and 1, but the multiplicity can vary. Okay. So please listen what I am going to say very carefully. That is very important. The roots of minimal polynomial and characteristic polynomial are exactly same, but the multiplicity is what changes. Okay, so maybe for minimal polynomials also eigenvalue will be like for example in this case the roots of the minimal polynomial is 0 and 1, and 0 occurs once, 1 occur once as a root. But for characteristic polynomial, the roots are still 0 and 1 only, but 0 can occur many times and 1 can occur many times. Okay. So as a set of roots, they are same, only the multiplicity can increase in the characteristic polynomial. That is a very important thing. So since the matrix is diagonalizable, so we can write A as A equal to P inverse under the diagonal matrix, where the diagonal entries of the matrix are eigenvalues. So what are the eigenvalues of A? We just saw that eigenvalues of A are eigenvalues of A are zeros and ones. Okay. So for example, A can have a eigenvalue 1 2 times, eigenvalue 0 3 times. Okay. Now since P is invertible, A and whatever matrix you get, these two matrices are conjugate. Okay, so conjugate matrices has the same trace, same rank, same determinant, same eigenvalue, everything is same. Okay, therefore A and this matrix are basically same. Okay, so what is the question? They are asking that if a matrix satisfies A square equal to A, then rank of A equal to trace of A. Okay, so for A, we want to prove rank of A equal to trace of A, but A and this matrix are similar. Okay, so to prove a result for A, we can very well prove result for this matrix. If you notice this matrix for any diagonal matrix with diagonal entries 0 and 1, for such matrix rank of A will be equal to trace of A always. Okay, for example, you see rank equal to 2 and trace also 2. Okay, so therefore we conclude that this justify it is given and the answer is true. Okay, so you can similarly justify the next question. So we just it is very simple. So the second problem is an exercise. Basically, it requires the same idea only. Okay. Okay, please comment your answer for the second problem, whether it is true or false. Again, the idea is same. Okay. So I think I'll stop here and I'll meet you guys in the third lecture on diagonalizable matrices. And then in the fourth lecture on diagonalizable matrices, we maybe in the third lecture itself, I'll try to start a Jordan canonical form. Okay. Okay, guys. Thank you.